Cheers. Okay, good afternoon, all of you. In today's session, we are going to do the topic redox reactions. That will be the topic for today. Okay, so what we'll do is that we will begin the session by first recapping what are the rules to find the oxidation number of an atom. So very quickly, what is oxidation number? Oxidation number is the charge that the atom will have, assuming that in a covalent bond, the more electronegative atom will take all the shared electrons to itself. So suppose you have water. So in this covalent bond, the electrons will entirely go to oxygen, and in this covalent bond also the electrons will entirely go to oxygen. So each hydrogen will become plus and the oxygen will become 2 minus, right? So each of the hydrogens will become plus and the oxygen will become 2 minus. So this is the concept of oxidation number. Now what are the rules to find oxidation number? Number one, so So the very first rule to find the oxidation number is that H2O2 N2P4 S8, right? H2O2 N2P4 and S8, they all have oxidation number 0 because this is considered the elementary form. So the elementary form of hydrogen is H2, elementary form of oxygen is O2, nitrogen is N2, phosphorus is P4, sulfur is S8. So because they are in elementary form, so the oxidation number will be 0. So that is rule number 1. So whenever an element is in the elementary form, the oxidation number is 0. That is rule number 1. Then we come to rule number 2. So rule number 2, Ca2 plus oxidation number is 2 and Cl minus the oxidation number will be minus 1. So calcium, like if it is a charged species, the oxidation number will be equal to the charge on the species. So Ca2 plus the charge is plus 2, so oxidation number will be 2. Cl minus the charge is minus 1, so oxidation number will be minus 1. Number 3, Number 3, the oxidation number of hydrogen is always +1 except in case of metallic hydrides. So hydrogen is always +1 except in metallic hydrides it is -1. Okay, so it is +1, but metallic hydrides it is -1. Okay, number 4, in case of oxygen, the oxidation number will be -2 if you are talking about a dioxide. Dioxide is the standard oxide like H2O. Then it will be -1 in case of peroxide, so H2O2. Then it is -half in case of superoxide like KO2. Then in OF2 it is +2 and in O2F2 it is +1. So for oxygen, these are the oxidation numbers in various forms of oxygen like dioxide, peroxide, superoxide, OF2 and O2F2. Okay, if it is a neutral molecule, then the total oxidation number will be 0. But if it is an ion, then total oxidation number will be equal to the charge on the ion, right? So these are the rules, and of course alkali metal oxidation number is always +1, and alkaline earth metal the oxidation number is always +2. So in case of alkali metal it is always +1, alkaline earth metal it is always +2. Now there is a topic that is exceptional oxidation number. Now this is a very important topic. Since this is a revision class, I don't want to give some very easy examples. Okay, this is the compound, tell the oxidation number. So I don't want to do all that. Rather, what I will suggest is we can do one thing. We can discuss the exceptional ones. Like exceptional ones means that there will be a compound in which the same atom will occur more than once, and both the times the oxidation number will be different. So we'll just discuss those because those are important. So So this is a compound C3O2. Okay, this is a compound C3O2. In C3O2, what happens is that this carbon is +2, this carbon is +2, but this carbon is 0. So in C3O2, you have 3 carbons and all of them don't have the same oxidation number. Now, there's a very easy way to derive this. I'll just quickly tell you. It's a very easy way. So what happens is that between this oxygen and carbon, there is a double bond. Double bond means that this oxygen is contributing 2 and this carbon is contributing 2, right? Now oxygen is more electronegative. So oxygen will keep its own electrons, and the electrons of carbon also it will keep, right? So oxygen will become 2 minus. Carbon will therefore, by the same logic, carbon will become 2 plus. These 2 carbons are both carbon, so 2 carbons are equally electronegative. So each of them will take their own electrons and that's it. So 0, 0. Then these 2 carbons, what is going to happen? They are also equally electronegative, so they will come out with their own carbon. So 0, 0. And finally this bond, the oxygen will take both of carbon and carbon will be shortage of those 2, so carbon will become +2. So you can see that oxygen is -2, carbon is +2, carbon is 0, carbon is +2, oxygen is -2. So this is a very easy way to derive the oxidation number when in the same compound you have multiple oxidation numbers. This method is very easily, you can apply this method. Okay, so have a look at this number 2 example. So in number 2, this is Br3O8. So bromine with 3 oxygens and then single bond bromine with 3 oxygens, and this bromine double bond oxygen. I don't want to repeat the whole thing again. Whatever I told you to do over here, just do the same thing over here. You will find this is +6, this is +6, this is +4. Just repeat whatever I said over here. That means when it is between the 2 bromines, 0, 0. When it is between bromine and oxygen, bromine will become, like it's a double bond, so bromine will become +2, oxygen will become -2. Just follow that logic. You will find this is 6, this is 4, this is 6. It's easy. You can do it on your own, right? Okay, now suppose you consider S4O6 2 minus. So Na2S4O6, H2S4O6, these are some famous compounds which contain this group S4O6 2 minus. So that instead of analyzing these compounds, we can just analyze this group S4O6 2 minus. Okay, so S4O6 2 minus. Sulfur, 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 4 sulfurs in a row, so obviously these two will be 0. I think you have understood the method by now. Then this is a double bond, so sulfur will become +2 because of this double bond. Because of this double bond, it will become +2. This is a single bond, so because of this single bond, it will become +1. So +2 + 2 + 1 is +5. And by the same logic, this sulfur is also +5. So I am not saying it in full like vivid illustration. I mean, by now, since this is a revision class, I think you have understood. So +5 0 0 and +5. Okay, then another example is the mixed oxides. That's another example, the mixed oxides. So if you consider Pb3O4, so it is 2:1 mixture of PbO and PbO2. So Pb3O4 has 2 moles of PbO and 1 mole of PbO2. So in 2 moles of PbO, the lead will be +2, and 1 mole of PbO2, the lead is +4. So this is another example where you have multiple oxidation numbers in the same compound. Fe3O4, 1 mole of FeO and 1 mole of Fe2O3. So FeO oxidation number +2, Fe2O3 oxidation number +3. So Pb3O4 lead can be +2 or +4. Fe3O4 iron can be +2 or +3 in the same compound. Like in Pb3O4 you can have lead both 2 and 4. In Fe3O4 you can have iron both 2 and 3. So in the same compound this thing can happen, and that is because they are mixed oxides. They are actually not the pure oxide, they are a mixture of 2 different oxides, that is why. Okay, have a look at this. All of you recognize this ethanol. CH3CH2OH, this is ethanol. So in ethanol, what is happening? This carbon has 3 hydrogens. So due to 3 hydrogens, it will become -3. Carbon, nothing, 0. And this carbon, due to these 2 hydrogens, it will become -2. But there is one oxygen. So due to oxygen, it will become +1. So -2 and +1 will become -1. So in ethanol, one carbon is -3, one carbon is -1. Okay, now let's have a look at the next compound, acetic acid. In acetic acid, 3 hydrogens, so it will become -3, carbon, carbon, nothing, so 0. And 2 oxygen, this is a double bond, and 1 oxygen, so +3. So this carbon is -3, this carbon is +3. Acetic acid. Okay, now consider this compound Ki3, right? Consider Ki3. So in Ki3, potassium is plus, and when you say I3 minus, so these two iodines both are 0, and this iodine is -1, okay? And this iodine, that I minus, is forming a coordinate bond with I2, right? So I minus is forming a coordinate covalent bond with I2. So this will be -1. These two are together as iodine molecules, so 0, 0, and potassium is plus. Is the interesting thing about this compound that this compound is one of the rare compounds where ionic bond, covalent bond, coordinate covalent bond, all three are present. So K plus and this entire thing is minus, so ionic bond. Iodine, iodine, 0, 0, covalent bond. And from I minus to this is a coordinate bond. So in the same compound you have ionic bond, you have covalent bond, and you also have coordinate covalent bond, all the three. So this is a compound which is Ki3, right? So this Ki3 is important because it has got this peculiar feature, and by the way, Ki3 has come in last year's 2020 JEE main exam also. So from competitive point of view also, Ki3 is important. So that more or less summarizes the exceptional oxidation numbers. That means different oxidation numbers of the same atom in the same species. Okay, next we come to the topic that is balancing the reactions by oxidation number method. So we'll just discuss that. So balance the total increase equal to total decrease. That is the thumb rule. When you want to balance the reaction by oxidation number method, balance total increase with total decrease. Like whatever is the total increase of oxidation number, you must balance it with the total decrease of oxidation number. So let's have a look at this reaction. C6H6 plus O2 is CO2 plus H2O. Let's see this one. So C6H6, carbon is -1, hydrogen is +1, and CO2, carbon is +4, oxygen is -2. So from C6H6 to CO2, the increase is 5, but there are 6 carbons, so total increase is 5, 6 are 30. Then from O2 to H2O, the change is 0 to -2, so decrease of 2, but there are 2 oxygens, so total decrease is 4. Now this is the thing, the total increase has to be equal to total decrease. That is the rule. You have to make that happen. Total increase and total decrease, you have to make it the same. So the total increase is 30, the total decrease is 4. You are allowed to reduce it by lowest terms. So 30 you can make it 15 and 4 you can make it 2. Like you are reducing 34 as making it 15 too. So as a result, what will happen is that here you will have to put a 2 and here you will have to put a 15. So if you put a 2 here, then on the right side there will be a 12 and here there will be a 6. So the point is that this is the most common method. This is the most common method to balance by oxidation number method. That is, make the total increase equal to the total decrease. Okay, now there is one important thing that you have to understand, that there are 2 exceptional reactions where you may get stuck while you are using this rule. One is if the compound is a mixed oxide, then there will be a problem. Why? See, if it is a mixed oxide, then what will happen is that the mixed oxide is made up of 2 oxides, like just GS को नहीं any time में ताले काल के उसमें ताले वही program. Okay, so if it is a mixed oxide, then there will be 2 different oxides and they both may not perform redox. Both of them may not perform redox. One of them may perform redox, the other one may not. So when the compound is a mixed oxide, then there will be some problem. The other is that suppose in a reaction there is a reagent which is having dual behavior. Like suppose there is a reaction in which you have an acid, inorganic acid, and it can also perform redox. It is an acid, but it can also perform redox. So it has dual behavior. So let us just see one example of each. Okay. Okay, now let's have a look at this reaction. MnO4 plus HCl is KCl plus MnCl2 plus H2O plus Cl2. Let's have a look at this reaction. In this reaction, you have MnO4, you have HCl. Now HCl, the thing about HCl is that in this reaction, HCl is HCl is actually getting oxidized. So HCl is playing the role of a reducing agent. In this reaction, I'll just explain that. So in KMnO4, the manganese is plus 7. In MnCl2, the manganese is plus 2. And in HCl, chlorine is minus 1. In Cl2, chlorine is 0. So what is happening is that the manganese is decreasing by 5. So it is going down from 7 to 2, so it's decreasing by 5. And chlorine it is increasing by 1. Chlorine is increasing by 1. But here there are 2 chlorines. In Cl2 there are 2 chlorines. So manganese is decreasing by 5, so this is plus 7, this is plus 2, and chlorine is increasing by 1, but there are 2 chlorines. Okay, so chlorine is increasing by 1, but there are 2 chlorines, like here there are 2 chlorines. So the suggestion is that because there are 2 chlorines, so you multiply this with 2. In that case, you'll have to multiply this with also 2. Okay, I'll just repeat again. Manganese is decreasing by 5. Chlorine is increasing by 1, but there are 2 chlorines. So you'll have to multiply 1 into 2. And manganese is decreasing by 5. So if you do this 1 into 2, then manganese also you'll have to do 5 into 2. After that, you will have to put a 10 here and a 2 here, right? Because 1 into 2 is 2, 5 into 2 is 10. So you have to put a 2 here and a 10 here, because total increase and total decrease has to be balanced, correct? Now let us go to the right hand side. So here you put a 2, here you put a 2. These 2 places you put a 2. And then you put a 2 here. So now what has happened, that we are only left with hydrogen. We are only left with hydrogen and oxygen. So oxygen there are 8. So suppose if I put a 8 here, because oxygen here it is 8. So if I put a 8 here, then I am getting 16 hydrogen, and here there are only 10. So let us summarize the status of this sum. KMnO4 coefficient will be 2, HCl coefficient will be 10, KCl coefficient is 2, MnCl2 coefficient is 2, water is 8, Cl2 is 2. But there is a problem. The problem is in the left side it is 10 hydrogen, but in the right side there is 16 hydrogen. Now the thing is, this is happening, like in spite of the fact that we have done total increase equal to total decrease, in spite of the fact that we have found out the coefficients properly, everything we have done, in spite of that the hydrogen is creating a problem. So why is it creating a problem? The reason is that in this reaction HCl is also playing the role of an acid. HCl is also playing the role of an acid. It is not only acting as a reducing agent, it is also playing the role of an acid. So how do we take that into account? So what we will say, that to balance the hydrogen, just increase the molecules of HCl, because that part of HCl you cannot get it from redox calculation. So to balance the hydrogen means there are 16 hydrogen, here there are 10 hydrogen. So just increase the amount of HCl by another 6. So that means HCl will become 16. But then chlorine has become 16. And over here chlorine is falling short. So you remove this 2 and make it 5. Because chlorine has started falling short. So chlorine has started falling short. So here it is 16. So here also it will be 16. 2 plus 4, 6 plus 10, 16. So this is one example that a particular compound is capable of dual behavior. It can behave as a reducing or oxidizing agent, and it can also behave as an acid. And when that happens, then by redox alone you cannot get the coefficient. So here HCl is acting like an acid. So you needed to add another 6 units of HCl to make the balancing perfect. And that 6 units of HCl you did not get by redox, you got it because HCl is an acid. Okay, let's have a look at two reactions. Pb3O4 plus 8HCl is equal to 3 PbCl2 plus Cl2 plus 4H2O. Pb3O4 plus 4HNO3 is 2PbNO3 whole twice plus PbO2 plus 2H2O. Now the thing is that these are looking like very two different outcomes. The outcomes are looking very different. Both are very famous inorganic acids. HCl is a famous inorganic acid, so is HNO3. So both of the reactions should follow the similar pattern, but they are not, right? Now let's discuss why this is happening. I told you whenever you have a mixed oxide, some problem will be created. First thing you have to understand that a mixed oxide is a mixture of two oxides. So even if the reaction is written with a mixed oxide, when you try to balance the reaction, you will have to consider the individual oxides which are, a part of that mixed oxide when you do the balancing. So first of all, let's consider the HCl reaction. So 2PbO plus 4HCl is 2PbCl2 plus 2H2O. Then, PbO2 plus 4HCl, PbCl2 plus Cl2 plus 2H2O. So what am I doing? I am breaking this Pb3O4 reaction like this, right? So 2PbO plus 4HCl is 2PbCl2 plus 2H2O, and PbO2 plus 4HCl is PbCl2 plus Cl2 plus H2O. So this reaction, I am breaking it into two parts. In fact, if you add these two, you will find it is coming the same as this. Like suppose if you add this plus this, it will come same as this, right? So So if you have a look at the first reaction, lead is plus 2, here also lead is plus 2. In both the places, lead is plus 2. And oxygen here is minus 2, here is minus 2, chlorine is the same. So this is a acid-base reaction. This is acid, this is a base, that is salt plus water. Acid plus base is equal to salt plus water. So this is a acid-base reaction. It is not a redox reaction. Let's look at the second one. Lead is 4, lead is 2, and chlorine is minus 1, chlorine is 0. So lead, PbO2, oxidation number of lead is 4. And you don't, in fact, we know thanks to P block that lead has got oxidation number either 2 or 4. Lead does not have any other oxidation number, it's either 2 or 4. And there is nothing above 4. So 4 can only go down. So 4 goes down to 2 and chlorine minus 1 goes to 0. So this is an example of redox. So now you can see that why the mixed oxides sums are a bit confusing, because the two oxides which are present, they both will play their role, right? So PbO will do the acid base and PbO2 will do the redox. So both of them will play the role, and that is the reason why you will find that the answer which you are getting is not easily understandable. I mean, how is this happening? It's not very clear. But when you understand that it is broken up into acid base and redox, two separate reactions, total is equal to this, then it only makes sense. Now, in contrast, let us look at the second reaction, HNO3. Now, HNO3 is considered to be a very strong oxidizing agent. It is very well known that out of the three famous inorganic acids, HNO3 has got the best oxidizing power. Okay, so 2 PbO plus 4 HNO3 is 2 PbNO3 all twice plus 4 H2O. Now let's understand what's happening. The problem is that PbO2 oxidation number is plus 4. So PbO2 in this reaction, it is acting like an oxidizing agent. But HNO3 is a very powerful oxidizing agent, correct? So PbO2 cannot react with HNO3 because PbO2's aim will be to oxidize, and HNO3 is also oxidizing in nature. Both are oxidizing in nature, so they cannot have a redox. That is impossible. On the other hand, PbO can have a reaction with HNO3, just like PbO had a reaction with HCl. What reaction was that? That was acid base. So PbO can react with HNO3 by a acid base reaction. That is possible. So when PbO reacts with HNO3, so that is why this is also acid base. This is also acid base reaction, right? So this is also acid base. So now you can see that contrasting reactions with HCl and HNO3 with HCl, it can behave like acid base and it can also do redox, but HNO3, it can only do acid base. So this is a very good example that when you have mixed oxide, then there is a bit of a confusion, right? So just remember, when there is a mixed oxide, then you have to be a little careful that you don't straight away try to do oxidation number method and balance. It won't work. Secondly, when you have dual behavior, like a substance can be oxidizing as well as acidic, then you can have this problem. Otherwise, by and large, oxidation number method will work. Now, oxidation number method, there are two important things you need to know in addition to the method we spoke about. That is, if the medium is acidic or if the medium is alkaline. Okay, now one of the best known oxidizing agents is potassium dichromate. So dichromate ion is highly oxidizing in nature, is acidified potassium dichromate, acidified sodium dichromate. They are considered one like the most powerful, definitely, alongside permanganate, potassium permanganate. So let's have a look at a very standard reaction. Cr2O7 2 minus plus Fe2 plus Cr3 plus Fe3. I'm not writing the full reaction, I'm just writing it in ionic form. So this reaction, it is taking place in acidic medium. I have already qualified that it is acidified potassium dichromate. Just excuse me 1 minute. Okay, so Cr2O7 2 minus plus Fe2 plus is Cr3 plus Fe3 plus. Okay, so this is the reaction. So chromium is going from 6 to 3, so chromium decreases by 3, and iron is going from 2 to 3, so iron increases by 1. So chromium decreases by 3 and iron increases by 1. Now what we have to do is we have to balance the total increase with total decrease. Now there is a problem that there are two chromiums, it is Cr2. So there are two chromiums. So because there are two chromiums, so therefore it will be decreases by 3 into 2, right? And here also you must write 1 into 2 because there are two chromiums. So in case of chromium, here it is written 2, but here it is not written anything, so you put a 2. And in case of iron, it is 3 2s are 6, so here and here you write a 6. So once again I am repeating, the chromium, the decrease is 3, but there are two chromiums, so the total decrease is 3 2s are 6, and iron the increase is 1. So because you are multiplying this with 6, so here also you have to multiply it with 2, right? So that is why what you will have to do is you will have to then put this coefficient 2 over here, because already this is Cr2, so you have to put a 2, and this is 3 2s are 6, so you just put a 6 over here, right? So now the balancing has happened, but oxygen is 7, right? The oxygen is 7. Oxygen is not balancing, it is 7. So to balance the oxygen, you have to follow the literature. What does it say? It says acidic medium. So to balance oxygen, first what you have to do is, whatever is the shortage oxygen, that many water molecule you will have to add. So you add 7H2O. Whatever is the shortage of oxygen, you have to add that many water molecules. So you add 7H2O. Then what you have to do is, the number of hydrogens which is extra on the one side, that many H plus you have to add on the other side. So 14 H plus, right? So once again, chromium, oxygen is 7, so you write 7 H2O. Hydrogen is 14, so you write 14 H plus. Now it has become absolutely okay. Okay, now there is another method that is known as half reaction, that means ion electron method. Okay, half reaction method, also known as ion electron method. So in this method, first you write the half reactions. Don't write the full reactions, write the half reactions. Like Cr2O7 2- is changing to Cr3 plus. So that means chromium is getting reduced. So only write this, don't write the full reaction. Now you put a 2 here. If you put a 2 here, then what will happen? The chromium has got balanced. Then there is a 7 oxygen, so you write 7 H2O, and here you write 14 H plus. Okay, that you know the reason why, because I explained to you that if you add whatever H2O, there will be excess of hydrogen, so to balance that you have to write H plus. Now here there is a plus 14 charge and a minus 2 charge. Plus 14 minus 2 is 12, and here there is a plus 6 charge. So here you add 6 electrons. Okay, so here you add 6 electrons. Then we come to the oxidation half of the reaction. Fe2 plus is getting oxidized to Fe3 plus, right? And is it balanced? Absolutely, it is balanced, nothing to do, it is absolutely ready. But here there is a charge of plus 2, here there is a charge of plus 3. So you will have to add one electron here so that both the sides have the same charge. Now in the end, the two half reactions have to be added, and the addition has to be done in such a way that the number of electrons should get cut. So you just put a 6 here, a 6 here, a 6 here, and then you draw a line and add these two reactions. So 14H plus Cr2O7 2 minus. So 14H plus Cr2O7 2 minus is 2Cr3 plus 6H2O. So we have got the same answer as we got by oxidation number method, right? So this is for acidic medium. If it is acidic medium, then you can do the sum by adding H2O for shortage oxygen, H plus for shortage hydrogen. If it is ion electron method, you will also have to mention the number of electrons which will get cut out during the last step. And if it is oxidation number method, then there is no question of electrons. Just add H2O for shortage oxygen and add H plus for shortage hydrogen. So this is if it is acidic medium. Okay, now we come to alkaline medium. Now see, in alkaline medium, I am deliberately choosing alkaline KMnO4. Actually, I would like to concentrate a bit on the famous reagents. Acidified K2Cr2O7 is a very famous one. Alkaline KMnO4 is also very famous. So MnO4 minus plus I minus is MnO2 plus IO3 minus. This reaction is taking place in alkaline medium, alkaline KMnO4. So manganese is changing from 7 to 4, so decrease by 3, and iodine is changing from -1 to 5, so increase by 6. So we can do one thing, we can reduce it, we can reduce 3 to 1 and 6 to 2. So that means according to that, you'll have to put a 2 here and you'll have to put a 2 here. Let's do it with oxidation number method. So you'll have to put a 2 here, you have to put a 2 here. Iodine seems to be balancing. There are 8 oxygens here. There are 4 plus 3, 7 oxygens on the right. So what you will have to do is that you will have to first take care of the oxygen. Okay, you have to first take care of the oxygen. So I am adding one H2O here. So 2 4s are 8 oxygens here. 4 plus 3 7 plus 1 8 oxygens on the right, because I have added one H2O. Now here there are 2 hydrogens. Okay, here there are 2 hydrogens, and here there are no hydrogens at all. So everybody has got balanced except hydrogen. Here there are 2 hydrogens, here there are no hydrogens at all. Now for balancing hydrogen, the rule is that whatever is the number of shortage hydrogen, you will have to add that many water molecule on the left side and the same number of OH minus on the right side. So here there are 2 hydrogens, here there are no hydrogens. So you will have to add 2 H2O over here and you will have to add 2 OH minus over here. That is the rule. That is the rule. So in alkaline medium, when everybody is over, then for hydrogen, whatever is the number of shortage hydrogen, you have to add that many H2O on the shortage side and equal number of OH minus on the other side. So here there is 2 hydrogen, here there are none. So add 2 H2O, and because you have added 2 H2O, so here you write 2 OH minus. Now it is fully balanced. In the end, just remember this is 2 H2O, this is H2O, so 1 H2O will get cut. So in the end it will be like this. So in the end it will be like this, 2MnO4 minus plus H2O plus I minus is 2MnO2 plus IO3 minus plus 2OH minus. Regarding the ion electron method, MnO4 minus is changing to MnO2, I minus is changing to IO3 minus. So regarding the ion electron method, here this is also Mn, this is also Mn, this is O4, this is O2. So to balance the oxygen you put at 2. So now oxygen has got balance, manganese has got balance, but there is a charge of -1. So for that reason you add one electron here. That's it. Now let's go to the other one. This is I, this is I. So balance. There are 3 oxygens here. So you add 3 H2O. Now because you have added 3 H2O, there are 6 hydrogens here. So here there is a shortage hydrogen. So you add 6 H2O. And here you add 6 OH minus. Now in the end you say like this, that there is a charge of -7 here and there is a charge of -1 here. So here you will have to Okay, so basically the thing is that in this I minus to IO3 minus, there are 3 oxygens here and there are no oxygens on the left. So I am writing 3H2O. Okay, all of you in the first reaction MnO4 minus to MnO2, I had told you that we'll have to put a 2 here, but if we put a 2 here, then manganese is not balancing. So therefore putting a 2 here is wrong. So in the first reaction you cannot put a 2 here, then manganese is not balancing. So you'll have to say that here oxygen is 4, here oxygen is 2. So you will have to, there is shortage oxygen. So you write 2H2O because there are 2 oxygen shortage. Now here there are 4 hydrogen. So on this side you write 4H2O and on this side you write 4OH minus. And here you put a 3. Okay, because here the total charge has to be the same as here. There is -4, there is -4. So once again there was a slight mistake in the first half of the reaction. I wrote a 2 here, that was not correct. Because Mn has to be balanced first. Mn is already balancing. Then comes oxygen. Now there is 4 here, there is 2 here. So there is a shortage oxygen here. So you add 2H2O. Because you have added 2H2O, so here there is 4 hydrogen. So here you write 4H2O and here you write 4OH minus. So total charge is -4, total charge is -4. So now what you do is you go to the other reaction. I minus is changing to IO3 minus. So here there is 3 oxygens. So there is shortage oxygen here, so 3H2O. Now this is creating 6 hydrogen. So you write 6H2O and here you write 6OH minus. There's a charge of -7, so here you write 6 electrons. Now the first reaction has 2 electrons, second reaction has 6 electrons. So you multiply the first reaction with 2. You multiply the first reaction with 2 and then you add both of them. So if you add both of them, then after adding both of them, this is what you will get. So you will get 2MnO4 minus plus H2O plus I minus is 2MnO2 plus IO3 minus plus 2H minus. That is the same answer, right? Okay. Now, one thing all of you must remember, because this comes in competitive exams very often. Okay, one thing okay, now one thing is that we are talking about potassium permanganate and we are talking about K2Cr2O7. They are all considered to be very powerful oxidizing agents. So in any redox, actually we also sometimes need to do volumetric analysis. So when we are doing volumetric analysis, that time you need to know that the equivalent mass will be what factor of the molar mass, that we need to know. So when we did, by the way, in this reaction, the reaction which we discussed just now, MnO4 minus plus H2O plus I minus is MnO2 plus IO3 plus 2H minus. In this reaction, it is behaving as alkaline but weakly alkaline. And in this reaction, the factor by which you will have to divide the molar mass to get equivalent mass, the factor will be 3. So that has to be calculated like this. Manganese is 7, manganese is 4. So from 7 to 4 the decrease is 3. So the factor means what factor? The factor by which you have to divide the molar mass to get the equivalent mass. So that factor has to be 3. In case of K2Cr2O7, there are 2 chromiums and the decrease in oxidation number is 3, but there are 2 chromiums, so the factor will be 6. That means in case of K2Cr2O7, to get the equivalent mass from molar mass, you have to divide by 6. Okay, so we have done acidified K2Cr2O7, we have done weakly alkaline KMnO4. So the next one is acidified KMnO4. So MnO4 minus plus I minus is Mn2 plus I2. This is the reaction. Okay, this is acidic medium. MnO4 minus plus I minus is Mn2 plus I2. I think we have got a fair idea about both the methods, oxidation number and ion electron. So let us do this sum by any one method. So let us do ion electron method. So MnO4 minus is changing to Mn2 plus, so manganese is balanced. Now this is acidified, so there is 4 oxygen, so shortage oxygen. So here you write 8H plus. Now on the left side the charge is +7 and here it is +2. So you add 5 electrons. Okay, here the charge is +7 and here it is +2, so here you add 5 electrons. And next we come to the second half of the reaction. So I minus is changing to I2, so you put a 2 here. So then iodine is balancing and then you write 2 electrons here. So now everything is ready, so just multiply this reaction with 2 and this reaction with 5. Now in this question, manganese oxidation number is changing from 7 to 2. So the factor will be 5. The factor will be 5. Factor means molar mass by factor will give equivalent mass. Okay, so the factor will be 5, and now you just have to add these two. So if you add these two, this is what you will get. So 10I minus plus 2MnO4 minus plus 16H plus is 2Mn2 plus 8H2O plus 5I2. So this will be the reaction with acidified KMnO4. Okay, then we have strongly alkaline. Okay, so if it is strongly alkaline, then MnO4 minus will change to MnO4 2 minus if it is strongly alkaline. So here you don't have to do anything, just you have to add 1 electron. Nothing else you have to do because balancing is already done. So here the factor will be 1. Now this chart which I have drawn over here, this whole chart, okay, I cannot tell you how many times in competitive exam the question has come from this chart. Many times. So you have to remember this chart. Okay, this chart will be helpful for any stoichiometric or volumetric calculation because that depends on equivalent mass. Now in case you are wondering how, I'll just quickly remind you that in acid-base neutralization and in redox reaction, there is one underlying concept. Like if you have an acid-base reaction, the number of equivalent of acid and number of equivalent of base must be the same for perfect neutralization. And in case of redox, the number of equivalents of reducing agent should be equal to number of equivalents of oxidizing agent for perfect redox reaction. So this is a very important concept. So the factors you have to remember, right? So K2Cr27 is acidified all the time, so factor is 6. KMnO4 acidified factor is 5, alkaline factor is 3, strongly alkaline factor is 1. Okay, then types of redox reactions. C plus O2 equal to CO2. So C plus O2 equal to CO2. This is called combination reaction. Just you need to know the names of all the types. So C plus O2 CO2, this is combination reaction. Then 2NaOH is 2Na plus H2. This is called decomposition reaction. Then FeSO4 plus Zn is ZnSO4 plus Fe. This is called metal displacement reaction. Then 2Na plus 2H2O is 2NaOH plus H2. This is called non-metal displacement reaction. 2Na plus 2H2O is 2NaOH plus H2. This is called non-metal displacement reaction. Then disproportionation 2H2O2 is 2H2O plus O2. So oxygen here is -1, here is -2, here is 0. So oxygen is oxidizing to O2 and it is reducing to H2O. So both are happening, so disproportionation. So these are the different types of reactions. Combination, decomposition is the reverse of combination, metal displacement, non-metal displacement, and disproportionation. So these are the type of reactions. Okay, in metal displacement reaction, I think you can see that there is a metal which is displacing another metal. Like iron is, zinc is displacing iron from iron salt, right? Now here there is a rule that the metal which is higher in the activity series will displace a metal which is lower. Now activity series is there in various formats. One is the very basic activity series which you saw in class 10. Then you have those electrode potential charts. What I will suggest is that I will give you a slightly bigger activity series compared to the one which was in class 10, and you don't have to at the same time mug up the whole electrode potential chart. So I'll give you a slightly bigger activity series. You can learn this, it will serve your purpose for any type of question. Okay, so just remember the activity series like this: sodium, potassium, barium, calcium, magnesium, aluminium, zinc, chromium, iron, cadmium, cobalt, nickel, tin, lead, hydrogen, copper, mercury, silver, gold, and platinum, right? So potassium, sodium, barium, calcium, magnesium, aluminium, zinc, chromium, iron, cadmium, cobalt, nickel, tin, lead, hydrogen, copper, mercury, silver, gold and platinum. If you can remember this list, right? If you can remember this list, I do not think you will have any problem, because this is a comprehensive list, because this is a issue that how much do you need to know, right? And do you need to mug up that electrode potential chart? That is impossible. What about the activity series which was done in class 10? No, that is not enough. That is too small. I think this one will serve your purpose, right? Sodium, potassium, barium, calcium, magnesium, aluminium, zinc, chromium. So you can see these ones were not there in the class 10 list. Chromium, cadmium, cobalt, right? So this is a comprehensive list. Okay. So in today's meeting, we have discussed what is oxidation number. We have discussed exceptional oxidation number, where you have multiple oxidation numbers of the same atom in the same compound. We have discussed balancing by oxidation number, balancing by ion electron method, both acidic medium and basic medium. We have discussed a very, very important factor chart for K2Cr2O7 and K1O4. Which are extremely important oxidizing agents, and we have discussed that what are the types of reactions, and finally a slightly comprehensive activity series which will hold good for any situation. You can crack any metal displacement reaction. If you know this activity series, I think this is it. You don't need to know anything more than this, right? So that's it. We have completed the session and we'll continue next day. Okay, I'll end this meeting. Bye all of you.